Hello, everyone. We are back studying chemistry. It's been a while. Hope everyone had a good break. And this is how we're going to do it for a little bit. So hopefully everyone was able to get a good understanding of Vesper theory from last week. And if you didn't, please go back and watch those videos. I think everyone got the homework turned in. But once we have a good understanding of Vesper, that three-dimensional structure, it's going to help us we're going to need it to be able to determine our next topic. And as a review, one other thing we're going to need is to remember what electronegativity is. So this is how well an atom shares electrons. So we're specifically talking about covalent bonds. So again, when it comes to electronegativity, we really don't care too much about these metals. We don't care about the noble gases because they're not forming covalent bonds. This is mostly going to be important for the non-metals, hydrogen over there. And the only thing you need to know is that it increases, electronegativity increases up and to the right, with the highest being fluorine. It's on a relative 0 to 4 scale. So fluorine is 4.0. Again, this is by saying it's relative, there is no unit. It's just comparatively to one to another. It's like if you score a 7 out of 10 on something, there's 10 is just we just say the highest. Well, here 4 is the highest. So we want to know how strongly does each element pull valence electrons that they're sharing. And so fluorine's the greediest, the most selfish. It kind of hoards. And as you go further down and to the left, it's more of a giver. It says, here, go ahead and take mine. So we need to know whether it's electronegative or not to figure out whether two atoms, when bonded, generates a polar covalent bond, or we'll just say polar bond. And so in short, a polar bond is when you have unequally shared electrons. So when this happens, when you have two elements, one with higher electronegativity like fluorine and one with lower like hydrogen, the fluorine is pulling more electron density towards itself, and it's going to act like it has what we call a partial negative charge. So it is electron rich. Even though they're technically neither of them are charged, HF is a neutral molecule. Since fluorine is pulling more electrons towards its atom than hydrogen, we have this is a lowercase delta negative, and that is a partial charge. Where hydrogen, it hasn't lost its electrons, so it's not positive, but we say delta positive because it has a lower electron density. It's electron poor. That's what the blue this density map is showing. So a polar bond is when you have unequally shared electrons. Now, not all polar bonds are alike. Up here we have HF, and fluorine being the most electronegative with hydrogen is very, very polar. But remember, on the trend, as you go down, electronegativity drops off. So the difference between these two is smaller in HCl than in HF. So this one, HCl, is not as polar as HF. And then bromine, which has even lower than chlorine, is even less polar. And then HI, where the difference is only 0.4, is only slightly polar. So generally, the further apart elements are on the periodic table, the more polar the bond is going to be. Whereas if they're right next to each other, or if it's the same atom, we might call it a non-polar covalent bond. So if it's non-polar, they are equally shared electrons. And that's because they either have equal, like hydrogen and hydrogen have the exact same electronegativity, so it would be non-polar, or carbon and hydrogen, the difference is only 0.4. And so when that value is really small, like less than 0.5, we can it's just as well just call it non-polar. It's not going to act polar. Now, I put a blue box around carbon and hydrogen because this is like an extra special example I want you to know because it is so common. And so anytime we talk organic chemistry, which is dealing with carbon, there's a whole bunch of hydrogen. And I want you to know that if you see carbon bonded to hydrogen, that bond is always considered non-polar because the electronegativities are just so close to each other. Oh, there's the bell. I guess it's time to start. The rest of that material was bonus. Now, going back to last semester, we defined different bonds based on whether it was with metal and nonmetal or two nonmetals, and would say if there are multiple nonmetals, it's covalent. If it's metal and nonmetal, it's ionic. Well, another way we can do that is by looking at differences in electronegativity. That's this delta En, difference in electronegativity. So if the value is less, if the difference of the two is less than 0.5, we can go ahead and say it's nonpolar. And so you have an even distribution. So this is a very mutual sharing of electrons. That's what we call a covalent bond. However, right now we're talking about if the difference gets to be between 0.5 and 1.7, now one element is pulling to a greater extent those unshared electrons. This is what we call the polar bond. So again, it's still technically sharing, however, it's unequally sharing. And so then when the electronegativity difference gets up to past 1.7, now here's where you get to where things we would normally call ionic. So if you were to look at any ionic equation or compound, and you look at the difference in their electronegativities, metals to nonmetals, you're generally always going to see it greater than the difference greater than this 1.7. So one element pulled so strongly that it took the electron away, and you have these completely separate electron clouds. So again, we kind of have this progression: covalent, nonpolar covalent, polar covalent, ionic. It's really just, we're looking at differences in electronegativity that really determines what type of bond is going to happen between two atoms. On this chart up here, it's showing a bunch of binary, just two element compounds sorted by electronegativity difference, and then on the y-axis, percent ionic character. So basically, the higher the percentage, the more it is taking electrons from one element to another, and the less it's sharing. And so if you look at the top, the ones with the greatest electronegativity difference, those are the ones you would normally say, yeah, those are ionic, metals and nonmetals, metals and nonmetals. And then down at the bottom, where there's a very small difference, it's nonmetals and nonmetals, and that's not surprising. But then there's some that kind of fall in the middle, like HCl and HF, and they have some kind of unusual properties. Now, normally we would look at HF and say, hey, that's a molecule because it's two nonmetals. And so, yeah, when it's pure, it is a covalent bond, but it's a very, very very, very polar bond. So much so that when you put it in water, it actually goes from being polar covalent to ionic. That's why HF and HCl, we know them as acids. So they dissociate and break apart when you put them in water, because when you put them in something even more, it polarizes the electrons enough that it goes ahead and becomes ionic. So again, we have this kind of sliding scale of differing electronegativity that can help us figure out what is polar, what is nonpolar, what is ionic. Now, we could also look at the Catellar triangle. This can further distinguish metallic bonding, because metallic bonds will also have very small differences in electronegativity, but the difference between covalent and metallic is the average electronegativity. So here we're looking at these three sections: metallic section, ionic section, covalent section. And so first consider bronze, an alloy of copper and tin. Now, both of them as metals have relatively low electronegativities, and the difference between them is only 0.1. So that would put them right about here. So alloys are going to have these small differences in electronegativity, but then on average lower electronegativities together. Calcium chloride, again, you would look at this and say, oh yeah, metal and nonmetal, that's ionic. Again, here we can see that because it has a difference in electronegativity of 2, and their average electronegativity is 2. And so that, again, puts us in this ionic region. And finally, CCl4 and 2 nonmetals, we would predict covalent anyway, but they have a difference of 0.5, an average of 2.8, and that would put it right here, right in this covalent section. So again, if we know the electronegativities, it can help us distinguish whether the bonding is going to be covalent, metallic, or ionic. Now, it's very uncommon to have a chemical with just one bond. So you can only have 2 atoms, and most are going to have more than 2. So here's simple carbon dioxide. Now, what I want you to already see with carbon dioxide is oxygen is more electronegative than carbon. So this bond is polar, but also this bond of carbon and oxygen is polar. And what's going to be important is to note that multiple bonds determine the polarity of the entire substance, molecular substance. So another way we can show a polar bond instead of the delta plus or negative is you can use this type of arrow. So it's written parallel to the bond and it's pointing to where the electronegativity is greatest. So think of this as electrons are drawn to this half of the molecule and there's a partial positive on this carbon. But at the same time, there is a second, where is it? There is a second arrow. So there's electron density pulled to this half of the molecule and to this half of the molecule. And because you have electron density on both sides, that's not polar. So this is a non-polar molecule, even though it has 2 polar bonds. So one thing we'll find is when we have things that are very symmetric, they tend to be less polar. So here is ammonia. It has 3 polar bonds. Again, the red in this diagram is showing electron density. And because it's trigonal pyramidal, it's not planar and flat, all the electron density is getting pushed to one side, and that makes it polar. However, if we change that nitrogen to a boron, boron doesn't have a non-bonding pair, and it's trigonal planar. And it has all its electron density pushed to all sides of this substance. And because electron density is over here and over here and over here, this is nonpolar. So knowing the electronegativity difference is one thing, but then you also have to couple this with VSEPR and these shapes to figure out whether something is polar or not. Again, the ones that are very flat and symmetric tend to be nonpolar. So again, these arrows we're showing, these are often called dipole moments, and it's just showing where electrons are pulled to. It's a quantitative measure of polarity. Now, you're not going to have to do any math here, but they do have magnitudes. So this is the Debye unit, 3.36 times 10 to the negative 30 coulombs times meters. So it's charge times distance. And when we, the Q is the difference in electronegativity, R is just the bond length. So we can calculate or measure these dipole moments. So here, ammonia is 1.46. So the larger this value, the more polar it is. Again, things that are polar behave differently than things that are nonpolar. For one, if you put polar molecules in an electrical field, they'll line up as you see here. So if they have these partial charges, remember, opposites attract. So positive, negative, positive, even though they're not truly charged, just having electrons leaning on one side of the molecule more than the other makes them have this kind of sticky connection, which is going to be really important and it is important for a lot of different reasons. For nonpolar things, they don't have these attractions. So I just told you there's 2 things that determined polarity: electronegativity difference and the bond length. And so here's an example showing both of them, HF and HI. HF has a greater difference in electronegativity. HI has a greater bond length. So if we want to know which one is actually more substantial or important, if we look at the measured dipole moment, 1.9 versus 0.38, turns out electronegativity difference has a much greater effect. So a bigger bond length might, again, that normally would indicate, oh, it's going to be more polar. But because iodine its electronegativity is so much smaller than fluorine, it tends to cancel out. So all this to say, when you're comparing polarity, really just which one has the difference in electronegativity. The length of the bond really isn't that big a factor. So here's a nice table of some other substances. So we have some that are linear, with HF being the most polar of 1.9 in this list. Water and H2S they're bent. Water again being more polar than H2S, and then a few others. These are all experimentally determined. You don't have to calculate them, but just you have to know the greater the value, the more polar it is. You'll generally see values between like 0 to maybe 3 to 4. The most polar thing ever created is all cis hexafluorocyclohexane, where there are 6 fluorines all on the same side of a 6 carbon ring with a dipole moment of 6.2. That's a fun fact. So on your homework, you'll see some problems that look like this. So it couples what we covered last week, Vesper, and then this week, polarity, to figure out is the molecule polar or not. So first, we need to determine geometry. So if we look at BF3, what you need to know is that there's 3 polar bonds, because fluorine is more electronegative than fluorine, and its shape is trigonal planar. There's 3 things, so anytime there's only 3 things attached, it's going to be trigonal something. And with 0 non-bonding pairs, there's no extra dots here, then it's planar, it's flat. So because these 3 all go out at the same exact angle, it makes those 3 polar bonds cancel out. And so because it's trigonal planar, it's non-polar. Now here is, in a similar sense, carbon tetrafluoride, 4 polar bonds. And hopefully you picked up from the video in the last week's lesson that when you see these lines, it's showing 3-dimensional depth. And all of the bond angles in this tetrahedral structure are exactly the same. So again, there's 4 polar bonds. However, because it's tetrahedral, they all cancel out. And again, it's nonpolar. Here we have NF3. Again, there's 3 polar bonds. But now here we have this tiny non-bonding pair, which instead of being trigonal planar, makes it trigonal pyramidal. And so because it makes these all bent to the side, to one side, they don't perfectly cancel, and this thing is going to be polar. OF2, again, there's 2 polar bonds, and hopefully you can even see here that it is bent. So if it wasn't for these non-bonding pairs, this thing would be linear. But because those are there, it makes it bent. They don't perfectly cancel, and it's polar. So if anytime there's more electrons on one half of the molecule versus the other, it's polar. Here, there's only 2 things. So first, there are no polar bonds because it's bonded to itself. And even if it wasn't, if it's linear, unlike this, it's still more likely to be nonpolar. So here's just a whole bunch of, I just threw a bunch of examples. Again, we want to predict the relative polarity. Is it polar or not? Now, I might ask you, is this thing polar? And what I'd want you to know is, well, because they have different electronegativity, the answer has to be yes. Chlorine is more electronegative than bromine because it's higher up on the periodic table. So you could draw an arrow going to the right. I would not expect you to know that the value is 0.5. That's experimentally determined. Now, I might ask you to know the value for this one. So go ahead. What's the value? That's right. It's 0. So anytime it's bonded to itself, there's no polar bonds. The dipole moment is 0. Water, again, if it wasn't for these non-bonding pairs, it would be polar because this thing would be linear, but because it's bent, it is polar. And again, a value of 1.85. Water is very polar. Here's hydrogen cyanide. Again, there's one polar bond. Notice there's also a non-bonding pair. So with all this extra electron density on one half away from this side, this one is very, very polar. Now, the next four, I want you to notice the next four are all tetrahedral carbon. Now, earlier, what did we say about carbon and hydrogen bonds? That's right, they're non-polar. So they're not really a factor here, but carbon and chlorine, that is a polar bond. So when you put one chlorine there, it makes it very polar. Okay, well, what about if you have two chlorines? Now, at first look, you might expect if one chlorine makes it polar, two chlorines might make it even more polar, but you'd be wrong. Instead, adding another electronegative atom spreads the electron density between them further out in this direction and that direction, making it less polar. If you have three chlorines, you actually have chloroform. Some people might know of. It's a very common industrial solvent. But with three chlorines, it's even less polar. And with four polar bonds, all going in opposite directions, it's completely nonpolar. So now it has a Debye unit of, or number of 0. So again, one polar bond generally makes it more polar than multiple polar bonds. So again, as you go to the right, notice how symmetric this one is. And so the more symmetric they are, they tend to be nonpolar because they cancel out. Here's acetone in nail polish remover. Again, there's really just one polar bond, and if that would go away, go away. Go away thing. It's very polar. Here we have fluorobenzene and difluorobenzene. Very polar, nonpolar, because they're pulling on opposite sides. Here we have boron trifluoride, and again, it's completely nonpolar when they all cancel. So last, to again, just practice this one more time. Here is some chlorine benzenes. So again, in organic notation, this ring actually looks like this, where there's these 6 carbons and 6 hydrogens. But in organic chemistry, you pretty much omit all carbon and hydrogen unless it's part of a functional group. So here, you're only showing the 3 or 2 chlorines. So if you'd like, hit pause and then determine, hey, what's the most polar? What's the least polar? Go ahead, do it. Hit pause right now. Pause. Do it. Hit pause. Okay. Okay, now unpaused, or you just listen. That's fine. We want to know, hey, what's the most polar? So first we're thinking, hey, where are polar bonds? And there they are. So anywhere you see an arrow, that is electron density being drawn to those atoms. So then we're looking for symmetry. So the most polar is going to have more electrons pulled to just one side instead of all sides. So A is the most polar because there's more being pulled on this half than on this half. C is the runner-up because there's some pulled this way and this way that go against each other, but then there's some pulled over here. And then both B and D are completely nonpolar. So whether you have 2 pulling at 180 or 3 pulling at 120 degrees away from each other, they're completely nonpolar. Again, we want to know after today, is it polar or not? Because that's going to determine how the molecule will act. You know, what one probably important application many of you have been taking advantage of is the microwave. Anyway, so if you like to, microwave your Hot Pockets or, I don't know, other stuff, make turkeys, they function based on polar molecules like water because microwave radiation happens to be absorbed particularly well by polar molecules. And so as they absorb, they move faster and faster. And remember, temperature is just motion. And so it heats them up. And this is the point where I would normally say, hey, let's watch this video. But because we're not here, you can just feel free to click on the link if you'd like, or if you don't, I won't judge you for that either. Okay, now anyway, I hope you enjoyed today's recording on polarity and how we determine polarity using both Vesper and electronegativity. Again, there will be a homework posted, and you'll have a few days to work it out. Please, please, please email me if you have any questions. I will probably post a time where if you want to Google Hangout as a way to have some face-to-face question asking, then we'll probably be doing that on Wednesdays. Other than that, again, email me all your questions and do the homework. Have a delightful